Hi, welcome to this video series on Introduction to Material Phenomena in Nuclear Environments. So in our last video, we discussed how neutron irradiation causes pKa's to occur, causing displacement spikes and lots of vacancies. So we've discussed neutron radiation, and we can also discuss how these vacancies can interact. So we have a neutron here, vacancy. We discuss how they formed how they can do a displacement spike and how they cause precipitates to form, and how these are responsible for irradiation assisted stress corrosion cracking, or IASCC. So these can actually cause some corrosion to occur, and this will eat into the steel. And we've also discussed how a neutron can transmute, for example, nickel into copper, nickel 62 into copper 63. So right here, nickel 62 into copper 63, and how that can cause embrittlement because of the formation of copper precipitates. So that's already discussing neutron irradiation in general. Alright, we've discussed neutron irradiation already. So how about other forms of radiation? Let's say like the alpha, beta, and gamma radiation. Okay, how will this actually affect our materials? And when you talk about a fission reactor, a nuclear fission reactor, we don't just have alpha, beta, gammas, and neutrons. We also have fission fragments flying around. So we have fission fragments. Fission fragments, for example, you have a xenon that's flying around very quickly. Or you have tin, you have other kinds of like cesium. All of these are flying around when the uranium splits into two, and these two have like several, like 80 MeV of energy per nucleus, and this will just ram its way into the lattice. Now what can happen? So we have we want to discuss how this will affect steel, how this can affect metallic lattices in general, and even the zirconium cladding. So let's talk about the alpha case first. So let's talk about alpha radiation. So we know already that these alpha particles are really helium nuclei. So they have 2 protons, 2 neutrons. So they have a charge of 2+. And after stabilizing, they will form helium atoms that are lodged into the steel. So when you have alpha radiation here, you'll start implanting helium atoms into the metal, be it steel or the cladding. So there'll be some helium atoms dispersed in these steels. And like the neutron, before coming to a stop, they will deposit a lot of energy into the lattice, causing a Pka cascade, or a displacement spike. However, this time, because it's charged, it does not have to hit the nucleus. So originally, you have a neutron, it has to kind of directly hit the nucleus in order to cause this Pka cascade. But with an alpha particle, it is charged this time. So when it's already far away, the nucleus can feel the electrostatic repulsion. So the range of interaction is higher. Yep, the range of interaction is bigger. It's more for alphas because of the range of the electrostatic force That means that the cross-section is way higher. So the frequency of this alpha interacting with the nucleus is a lot higher by virtue of its charge. So let's have this alpha particle, and like the primary knock-on atom cascade we discussed earlier. So we have a pKa. Some of the particles flying through the nucleus, flying through the lattice, are the pKa's generated by a neutron and whatever. These are stopped very quickly because they are charged, and it can either cause the two regimes we have discussed. It can slow down via electronic stopping, where it ionizes the atoms along the way, and there's also the Pka cascade. Pka cascade. It transfers about this much energy. Remember the 4 mm over m plus m squared? That's the maximum, and then we just put half in front of it. That's the fraction of energy being transferred. So the alpha particle will also interact in the same way in a very similar way like this pKa, because it is charged like the pKa, and the alpha particle itself can also knock onto some atoms and cause more Pka cascade. So the alpha can go into a lattice. It'll knock onto the Pka. So the alpha comes in, knocks onto the Pka will knock into the lattice. This is very similar to what we have discussed already. So once it comes to a stop, or you can call it thermalized, what does it do? In comparison to our neutron, the neutron tends to get absorbed or transmute some of the atoms inside the lattice. So the other thing is that it can decay. That was not discussed before, but a neutron can beta decay into a hydrogen atom, which is essentially a proton plus electron plus antineutrino. So a neutron can decay into a hydrogen atom, but this is a half-life of 10 minutes, 10.5 minutes. Alright, so the more likely reaction it gets is the absorption reaction. But for the alpha, it will not get absorbed in case it comes to rest as a foreign interstitial atom inside the lattice. So let's call this an alpha. So it will get lodged inside there. If you find a vacancy in the lattice, so let's say you have this here, you have some alpha here, it will start migrating towards this vacancy. So alphas will tend to migrate towards a vacancy, and when they cluster together, they can form helium bubbles. These are also a obstacle to dislocation motion. Okay, and it will cause embrittlement as well. Now I've inserted a paper in the description for your reference. So yes, helium embrittlement. This is quite an issue for nuclear plants because of the alpha radiation that comes, and the alpha radiation will deposit helium into the lattice. Okay, and that causes barriers to dislocation motion and therefore embrittlement. So let's glance at the other two. What about beta radiation? So the beta radiation, we can talk about beta minus or beta plus. So for example, cesium-137 will decay into barium-137 plus electron plus antineutrino this is a beta minus decay. So a neutron turns into a proton, and then the negatively charged electron, this will carry a lot of the energy along with this as well, but here we are just concerned with the electron. The antineutrino is not charged, so and doesn't really interact as much. But this neutron, this electron is very highly charged. It can have energy of several keV or sometimes even MeV. But usually the keV range is more of the norm. So again, what does this beta electron do? As with any charged particle, it can cause ionization. That's why it's called ionizing radiation. And the second thing it can do is that we can have a Pka cascade, simply by virtue of this being charged. So once the electron, so when the electron is interacting with the nucleus, we know that it is attracted. So how does it bounce off or transfer its momentum? Well, it doesn't quite transfer it via bouncing off. Let's say you have an electron that's attracted to the nucleus, and then it will go this way. So we have a nucleus here. This is a fast flying electron. So when the electron is deflected in this direction, the nucleus will tend to be deflected in this direction because of the conservation of linear momentum in this direction. P is conserved in this direction. So when the electron flies here, we will know that the nucleus the nucleus is being deflected this way because of the conservation of momentum. Okay, and that's how it can cause a Pka cascade. So now this nucleus has some kinetic energy being imparted to it by this electron. So that's how it happens. And after that, this will come to a stop, and then this will try and find some positive charge, and then it will migrate there. Nothing that interesting. What about this anti-electron? So this is a beta plus particle. A beta plus particle, which is an anti-electron. What will happen to it? Well, an anti-electron will usually find an electron, and you'll produce two gamma rays. Each have about 511 keV. Because antimatter and matter, they annihilate each other, and they'll form into energy. So these are the photons that come out. So that's it for beta plus radiation. So what about gamma rays in general? Okay, what about gamma rays in general? So there can be this annihilation gamma ray. It can be any kind of gamma ray. So this is usually not charged. But how does it interact with the matter? Well, gamma rays can actually do a few things. The most common of them being Compton scattering. So what's Compton scattering? Sounds very complicated, but it's not that. It's pretty simple. What happens is that this gamma ray, while it doesn't interact that much with the nucleus, it can still cause ionization to occur. Okay, or basically by knocking off an electron. So this gamma ray imparts some of its momentum and energy into this electron, and this electron will fly off this way. And this is what Compton scattering is. Now once gamma ray imparts its energy into the electron, what happens is that this electron will have increased energy, and when this electron has increased energy, it can either cause ionization or Pka cascades. So yeah, that's what can occur. Alright, so when the gamma ray scatters off an electron, the electron gains energy, and it can start doing the same things like what a beta minus electron can do. So any moving charge particle can cause a Pka cascade. Now what about the fission fragments? Okay, before I go there, some of these some of these gamma rays interact with electrons, gamma rays or X-rays, they interact with electrons. These electrons, the secondary electrons, are called Auger electrons. Okay, Auger electrons. That's just to introduce a term. So some of these electrons, they are called Auger electrons. So if this electron is inside the innermost shell of the atom, one of the very innermost shell of the atom, and is knocked off by, let's say, an X-ray or gamma ray, okay? Actually, no, that's not an auger. Okay, auger effects is a bit more complicated. Sorry, I made a mistake there. Anyway, so yeah, the inner shell vacancy of the atom is accompanied by emission of an electron by the same atom. So, okay, let's explain the process a little more accurately. So you still have this Compton scattering that occurs. So let's say you have an atom, you have two of these electrons, the gamma ray comes in, scatters this off. So what we have are, okay, let's say you have a carbon atom like this, or maybe something bigger. So now there's a vacancy here, and this is the nucleus. The electron has been scattered off. Okay, so when the core electron is removed, electron from higher energy can fall into this here. So if we use an energy diagram, when this energy fall, when this electron falls from a higher shell to a lower shell, a photon is released. Okay, and this photon can also knock off other electrons, let's say in other shells. And this causes an electron to get ejected. Now these secondary electrons are called Auger electrons. Okay, so you have these primary electrons being scattered off, and then you have Auger electrons being scattered off as well. So it's a very messy kind of a thing. Okay, so we'll leave that for other kind of discussion, but this is just to give you some idea of what can happen when a gamma ray interacts with the electron shells. Now let's talk about fission fragments. So again, the idea is the same. You have xenon or cesium that comes straight from a nuclear fission reaction. Energy is about 80 MeV. Okay, so it's flying around really quickly. And we can imagine that when they come into contact with the cladding, because they are charged, they will cause this displacement spike again. They will cause a displacement spike again. And they have a Pka being generated, and then you have that whole cascade happening. And then some of these fission fragments are lodged into the cladding itself. Okay, so the cladding is just outside the fuel. Okay, the fuel is here, so the xenon atoms can come from here right into the fuel, and these are known as swift ions. So we will have a displacement spike being produced. We have displacement spike being produced, And then, because they are radioactive, we will have more radiation damage. Because, okay, let's say you have this lattice, the swift ion gets lodged in here. There's a fission fragment here. Now this fission fragment will decay. It can release alpha, beta, or gamma radiation, and it will cause all these things that are described earlier. So if it releases a gamma ray, it can do some ionization, Compton scattering, etc., etc. And you can see that fission fragments, they can cause quite a fair bit of damage. So these at most, they will be trapped in the cladding, and it is not likely that they'll make it all the way into the reactor precious vessel steel, which is not likely because of the nature of their charge, so they won't escape the cladding usually. Yeah. So you can see that the interaction of a fission fragment, the alpha particle, they're quite similar. It's just that their masses and energies are different. So you come to see that once we understand neutron damage, the material damage caused by other forms of radiation and even the swift ions, it's not that difficult to understand. So thanks for watching. I'll see you around next time.